All right, well, good morning, everybody. To today's on comparing simulation measured data through extractions. Kind of a weird time right now. I'm conducting this webinar from home. Hopefully I have enough bandwidth to have a nice smooth stream for everybody. So if you do notice any stuttering or jitteriness that you think is due to my bandwidth, just let me know in the chat window and I'll try to slow down the presentation and let things catch up. So today's webinar presented by me, Scott Fowler. I'm the product manager of TechPlot 360. I've been with TechPlot for quite a long time now, since 1999. I've really enjoyed being here at TechPlot. One of my favorite things about this job is being able to interact with such an intelligent crowd of people. So thank you for making my job so interesting. If ever you have a question, want to know something about TechPlot, have a suggestion for the product, feel free to contact me at the email address that you see there. You can also access our support staff. We have a couple of people on staff and they'll be able to get answers to you very quickly as well. That's support@techplot.com. So I do ask that you participate in today's webinar. You can ask questions. I will take questions at the end of the webinar. So feel free to ask questions during, but I will get to them at the end. If for some reason I can't answer your question or we run out of time, we will follow up with you via email. So never fear, we'll get out and reach out to you. There will be a recording of this webinar. We're pretty quick about getting the recorded webinars available shortly after, so look for that in the next day or two. In your email inbox. There are some scripts and some data that we're showing in this webinar that's going to be available for download when the webinar gets posted. Okay, so today's agenda, we're going to talk about how to get more out of your simulation data by using data extractions. So a lot of people know TechPlot as having great 3D views. We do a really great job at showing you your simulated data in nice, vibrant 3D views. But we also know that a lot of engineering decisions are made looking at single values or line plots. So that's where data extractions really come into place. So we're going to show you a few techniques for extracting. The first three techniques, extract from polyline, extract precise line, and extracting a slice from a slice, can all be done directly through the TechPlot 360 user interface, and we'll show you how to do that today. And then we have a fairly new function that we've added to our Python API called probe on surface, and this has been really useful to our users who are trying to compare wind tunnel results with simulated results. So they'll oftentimes have a very specific XYZ location that, say, represents a pressure tap, and they can use probe on surface to get the nearest surface location to that XYZ location using this function, and we'll show you how to use that script. And then we'll open it up for Q&A. I expect this webinar to run until 10:30 to 10:45. I think we've scheduled for a full hour, so we may get you out of here a little bit early and should have plenty of time for questions at the end. Okay, so without further ado, let's jump right into the demo. We're going to be using today some data that is included with the TechPlot 360 installation. This is the Onera M6 wing that was simulated using SU2. We have some measured data as well, which in this image here you can see the spheres represent the locations of the measured data or pressure tap locations when done in the wind tunnel. So let's bring up TechPlot 360. Again, the Onera M6 wing, this data set, let me just bring up File Explorer really quick. So in the TechPlot 360 installation, I'm not in that directory here, but you can look for the Onera M6 wing. And then we also distribute the experimental data. Now, one thing that you'll notice with this experimental data is it's been normalized. So in the download that you're going to get, I have a Python script that uses our PyTechPlot API, and I've taken that normalized data and really fitted it to the wing. So you can run that script to take this experimental data and fit it to the wing. So it lies right on the wing, which is going to be useful for our demonstration today. All right, so I'm going to turn off the scatter layer so we see just the wing. And first, let's look at a way of extracting data using extract from Polyline. So this is a really nice tool for just kind of a quick and dirty view of what's going on the surface. So I select the Polyline tool, and I'll just click 2 points along my wing, along the leading edge here. And so I've clicked once, clicked twice, and now it's just kind of hanging about here. I can hit right click to finish drawing that. And now I have my polyline. And when I select that, I can right click, I'll say extract points. This gives me the option of how many points along this line do I want to extract. So I can extract an even number of points spaced, so 200 spaced evenly along that line, or I can extract the points that define the geometry. I defined this only by 2 points, the start at the end. So if I want any of the data in the middle, I'm going to select regular points along that geometry. And I'll hit extract. The extraction is now complete. And let's look at the dataset information dialog. You can see that I now have this zone called extracted points with 200, and it has all of the variable values associated with it. To plot these results, I'll use our create new frame tool and just drag, click and drag to create a new frame, and I'll flip this frame to XY line. And what this is now going to do is it's going to inherit the data that was in this frame, and I want to look at Y on the x-axis, and let's look at pressure coefficient on the y-axis for the extracted points that we just got. And so now here's my line plot. So nice, easy way to get a quick view of your data using the extract from Polyline tool. Just a couple of notes about the extract from Polyline tool. You can do arbitrary polyline. So here I have a number of points, and I could extract from this. Say maybe you do geoscience, and you want to extract points on the surface of the ocean up an inlet or up a river. You could use a tool like this to kind of follow the path of that river. So nice capability there as well. And if you do have transient data, when you have that polyline selected, you can go to Data, Extract, and you can extract this geometry through time. So it will extract, and then you'll have a transient result at that point. Okay, just a quick note about this tool. When I do have a polyline here, the orientation of my data matters. So let me turn off the mesh, and I'm left with just the polyline. If I rotate my plot, I'm going to get a very different set of points. So what we think of TechPlot as extracting these points by shooting a ray from your eye through the screen, through the monitor, through that point, and then hitting the surface. So you can see right now I'm going to get a point right up this line, but if I rotate my plot slightly, I'm going to get a line in a very different location. So this is important to know when you're doing this in a scripted manner. If you're running TechPlot in batch, you want to make sure that you always have the orientation of your plot the same relative to where that polyline is. Okay, so that's extract from Polyline. Now let's look at the next one, which is extract a precise line. So if we go to Data, Extract, Precise Line, this tool is nice because it allows us to specify an exact XYZ starting location and ending location. This is really ideal for extracting data from a volume because we're specifying these exact XYZ locations. Extracting from a surface like this has similar issues to extracting the polyline geometry, that it is dependent on the orientation of the plot. So I'll just demonstrate this again. So let's say I want to look at a line that goes from the leading edge to the trailing edge. So I'll just use the probe tool. click here. So leading edge, I can copy and paste out of the probe dialog. We'll just hit Control C, Control V. So that's leading edge, and then let's probe again at trailing edge. And again, we'll Control C, Control V. Okay, and we'll just do 100 points evenly distributed along that line, and we'll go ahead and hit extract. Let's turn on the mesh again. You see that I have the line from our previous extraction and the line from this new extraction. Now, if I rotate this plot slightly and extract again, let's rotate around like this. You see that, of course, an airfoil has some shape to it. So this line that I'm extracting actually goes from this point to this point. So in this view, if I hit extract, I'm going to, again, shoot a ray from my eye through the screen and hit the surface that is along that line, which is actually going to hit the inside of my wing here. So if I hit extract, you're going to see I have this line inside my wing, and then as we rotate out, you can see that it is all the way back here. So again, extract precise line, very nice for very specific locations of your extraction, but when extracting from a surface, it uses that same tech of shooting a ray from your eye through the screen to that location. Now, if you are extracting from the volume, those XYZ locations are always going to be within the volume, so you're going to get it right where you would expect it. Okay, let's. I'm going to open this layout again. Start from scratch. Okay, so that is extract precise line, extract from a geometry. Now let's look at extracting a slice from a slice and why you would want to do this. So let me turn on my slice layer. I'll turn off scatter again. So here I have a slice going through my volume domain. See that near the surface of the wing in the boundary layer, my cells are very, very small. And a technique like the extract precise line, where I have a regular distribution of points, works okay, but it may not capture, it may be too spread out in the region where my cells are small, and then be over-specified in the area where my cells are large. So we can approximate that just by doing my geometry tool, and we'll show this. So let's extract points, and we'll go 200 points along here, and we'll turn on scatter again. And if I zoom way in here, you can see that while I have 200 points evenly distributed along this line, the resolution between those points is not fine enough down here, and then it gets too fine as my cells get larger. So I've overspecified the number of points that I want to extract. So a good way to do this is to extract a slice from another slice, and then I'm going to get the exact grid intersections. So let me just delete this zone that I just extracted, and we'll do Control F, and we'll turn off scatter again. Here I have a slice. I can right click here and hit extract, and I'm going to just say yes, I want to extract that. Okay, now you see that we have some stitching here because I have a slice that's being drawn at the same time that I have a zone. These are coincident. So when we send all these commands to OpenGL, these cells are exactly in the same spot. So OpenGL just picks one or the other. So let's turn off, or let's change this slice now to be an X plane. And what I actually want to do is I want to extract a surface. I want to extract from the surface of this other slice. So now I have a line. You can see that it's also, this slice is also passing through the wing well, I don't want it to pass through the wing. I just want it to pass through this slice that we extracted. So we will, in the zone style dialog, briefly turn off the wing. And if I zoom way in here, you can see that we have a line going right through all of our cells. And I'll extract this slice now. And then if I turn on the scatter layer, we'll see that this extracted line, let's turn off the slice, we now have points at each one of the grid intersections. So this is nice. This will capture all of the information in the boundary layer just perfectly with the cell density that you have. So a very nice technique for capturing that grid density and avoiding over specifying where your grid is thin. So that's extract a slice from a slice. Okay, so that's 3 techniques really quickly we showed you in about 10 or 15 minutes. So now let's start fresh again, and we'll dive into the Python portion of this. So one of the things that I want to do is I want to extract the pressure coefficient information at each one of these locations from my simulated data. So these points that I'm showing here, this is measured data. And let's just zoom way in here on a couple of these. Let's go up towards the leading edge. And if I hit O on the keyboard, that will change the center of rotation right to where my mouse is, and then Control right click and I can rotate about. And you can see that as I zoom in, you'll see that this measure data is not exactly on the surface. So if I were to try to probe at this XYZ position and get information from the surface, well, it's not going to hit the surface. So what is our solution? Our solution is to use this new Python function called probe on surface. And what that function does is it will take an XYZ location and it will find the nearest surface location independent of the view. So it'll use the normals of the surface data to try to find that nearest location. Okay, so let me just show you some of the Python documentation if you're not familiar with it. If you're not familiar with PyTechplot, this is a Python API that is available to use with TechPlot 360. It's pretty interesting. You can use it in a couple of ways. You can use it connected to TechPlot 360, so you can actually drive a live running 360. You can also use it entirely in batch mode. So say you have a lot of files that you want to process on a cluster, run it away to run. You do need enough licenses to run multiple instances simultaneously, but it is a very powerful tool. Gives you access to the raw data, which I'll show today. It is a separate installation. We have great installation notes. If you have Python 2.7 or 3.4 or 3.5 and newer, sorry, you can use PyTechplot. It's just pip install PyTechplot on most machines, and we have a lot of examples. So the function that I'm going to show today is called probe on surface. We have a good set of documentation here that you can reference, complete with example code showing how to apply data to the function and get data out of the function. So we spent a lot of time on the documentation and found that that's been quite helpful to a lot of people. Okay, so let's do Control F and let me turn off the mesh. Okay, so here's what I'm going to do. I'm going to run a script that I've already written, and then I'll show you how the script was written. So first, to allow a Python script to drive a live running 360, we go to the scripting menu, PyTechplot connections, and we make sure that accept connections is checked. We actually use sockets to communicate between Python and TechPlot 360. So we're communicating with sockets over port 7600. And then I'll bring up my command prompt and I'll just run my script, probe on surface. And so what this is going to do is each one of these zones that defines the points, we're going to find the XYZ locations, and then at each XYZ location, we will call probe on surface and then construct a new zone within TechPlot. So if we go into the dataset information dialog, we now see that we have the probed values. So let's go into zone style and we'll turn these on. We'll change the scatters to cubes, and let's change the size to 1.5. And so now you can see that these have these are fairly coincident with the spheres. So we've found locations that are awfully close. Now, if we zoom again way in here, we should see that the cube is actually on the surface, whereas the measured location is slightly off, but it found a location that is very, very close to that, using the normal of the cell to identify the closest location to that sphere. So we'll zoom back out using Control F. And let's just, now we want to analyze this data. So let's look at it in a line plot. So I'll create a new frame. And we'll go XY line. So this again inherits the data. I'm going to say x-axis for all linear zones, x versus y for all linear zones, and we want to look at x versus pressure coefficient. And we'll go to the axis dialog, and for the y-axis, let's reverse. And let's just focus in on a couple of one of the sections here. So I'm going to look at 0.8, and we'll do a Control F, and let's put on the line legend. Okay, so now we have a nice quantitative view of our data, and one thing that is interesting to point out here is that we do have a pretty big variance between our simulated data, so that's this probed line, and our measured data. So where is this actually on the model? So let's go back to our 3D view, and we'll do a little calculation to highlight where that is. Let's say bring to front. And in the zone style dialog, let's again just focus on 0.8. So we'll say show selected only, and then turn our wing back on. So where is that data that is slightly different? So let's go into data, alter, specify equations, and you can see I preceded an equation here. So I'm going to compute a new variable called CP_diff. So this is going to be the difference in pressure coefficient between the 12th variable in my data set. So this is a little shorthand here, which is B12, pressure coefficient. I could also write this as pressure coefficient. Hopefully I got the spelling right. I'm not going to take chances in a live webinar, so we'll go back to V12. And I want to subtract from zone 6, which is section at 0.8. I want to do the alteration only for this selected zone. So for this zone, I'm going to be doing the difference in coefficient of pressure between these two zones. So let's go ahead and hit compute. And then let's color the cubes by that difference in pressure coefficient. So we'll go into the contour dialog, and we'll set up another contour group for CP_diff, and we'll set the levels from -0.1 to 0.1 with 11. So this is going to put 0 right at the center. And let's select a different color map. Let's choose kind of this orange and purple. Reminds me of purple and gold. I'm a UW Husky, so that's kind of fun. And then we'll go into the zone style dialog. right-click and select contour group 2. So you can see we now have our legend here, and now we can very easily see where we have a difference between our measured data and our simulated data. Okay. Now these scatter symbols are sized by a percentage of the frame. One nice thing that you can do in TechPlot, you can actually do a zoom on the frame itself. You see I'm bringing the whole frame closer to me. So it's kind of like if you're holding onto a piece of paper, you're bringing that paper close to you. I'm holding down the Shift key and pressing and dragging the middle mouse button. That brings everything closer. So now I can really see where those differences are and get a quantitative understanding of the difference between the measured data and the simulated data. Okay, so I'll do Control Shift A. That's going to fit all my frames back to my view, and Control F, and that'll fit my wing. Okay, so let's take a quick look at the script, what that looks like. So here's my probe on surface script. First thing I'm doing is I'm importing a Python package called NumPy, which is a mathematical package. Has a lot of great functions for matrices, arrays, and other mathematics. I'm bringing in the TechPlot Python package, import TechPlot, and I'm aliasing it to TP. So you see every time you see TP, I'm referencing using TechPlot. The first command here, TP session connect. So that's going to tell this script to connect to the live running version of TechPlot 360. Every function call, because I'm connected to a live running 360, every function call I make is going to try to update TechPlot 360. Well, in this situation, I'm doing just basically just a lot of introspection of the data and math, and I don't really need to see the view update until the end. So I'm going to suspend the user interface. It'll make the script run a little bit faster as well. And then within here, I'm going to get a hold of the current frame, the data set in that frame, and then I get a list of zones that start with the word section. Now these are my measured data. So if I bring this over to the side, let's bring data set info dialog up again. You can see that my measured data all starts with the word section. That's what I'm doing there. So that gets that list of zones. Then I just do a loop over that and get the points, the XYZ locations associated with these sections. I get that into an array that gets passed off to the probe on surface function. And probe on surface, if I had multiple surfaces and I want to limit the search to a single surface, which I'm doing here, I want to make sure that probe on surface only looks for data on the wing surface. So I'm limiting that search, and then it's going to give me the results. Through a little bit of magic with NumPy, I'm able to reshape the results such that they're very easy to pass back off the TechPlot to create new data. So that's what I'm doing here. Now that I have my results, or those probed results, I'm adding a new zone to TechPlot called probed dash, and then the name of the original. So you can see that exactly here. And then for each of the variables in the data set, I'm putting the probe results into this resulting zone. So fairly short script. For those of you that are fairly new to Python or some of the concepts of TechPlot 360, this might look a bit complicated. And if you need to do work like this or need any help with Python to use TechPlot not only for visualization but additional data analysis, contact our support staff. We're here to help. Look at the documentation. It's a great resource. But definitely, if you're paying us for maintenance, if you have that Tech Plus contract, you have the rights to get a hold of us and get some help, and we're happy to help. Okay, so that's a description of the script, and that's the end of the live demo portion. So let's go back into the PowerPoint and close out the webinar. If you have any questions, you can go ahead and start typing them now. So in summary, we've looked at extract from Polyline. So again, that was drawing that Polyline geometry on the screen. It's really great for extracting from surface data. In this case, I showed extracting from a 3D plot. You can also use it in 2D very easily. It is view dependent, so if you are doing this in a scripted fashion, you have to make sure that your view angles are going to be the same and consistent when you're using that. You can specify exact coordinates, much like the extract precise line. You can define extract coordinates in tecplot macros or via Python. Those coordinates are going to be in a 2D space though. So because it is a geometry drawn on the frame, typically those are drawn in what we call the frame coordinate system. So if you need points that are in a 3D space or very exact, you can use extract precise line. And that's, again, a very good tool for extracting data from surfaces and volumes. When extracting from surfaces, again, it is view dependent, so make sure those rotation angles are consistent. Extracting a slice from a slice we talked about, and again, this is good to capture the exact grid intersections if you want that information that's in the boundary layer. It is not view dependent, so view independent. And so you don't have to worry about the rotation angles of your data there. In the case that I showed, when we did extract data above the wing surface and below the wing surface. You could couple this technique with our value blanking capability to, say, limit the extent for that slice. You could use value blanking to limit any of these extractions. So that's a nice tool as well. And then, of course, we went through and did probe on surface, which, again, Python only. You saw the documentation, so pretty good documentation there, and a very useful tool when those XYZ coordinates don't lie exactly on the surface, but you do want to get data from the surface. Okay, so it looks like a couple of questions have come in, so give me just a minute to read these and then I'll try to respond. Let's see. Can you plot it on the line arbitrary axis direction as the independent variable instead of one of the principal axes? Yeah, and the horizontal axis in the XY plot will be distance along the polyline rather than Y. Yeah, so that's a good question. When we do our extractions, we don't include a distance variable, but that you could calculate a distance variable fairly easily with a Python script and then use any other variable on the X or Y axes. One of the interesting things in the XY plots is you can also have multiple axes. We allow up to 5 X axes or up to 5 Y axes. So you can actually have data of multiple resolutions or multiple quite different varying magnitudes on X and Y axes. We do also support log axes. So yeah, distance, you'd have to calculate that after the fact because we don't include a distance variable in the extraction. And then another question in alter equations, why have you used V12? Is V12 already defined as pressure coefficient? Yeah, so let me just go back to tecplot 360. So V12 here, bring up the specify equations dialog. So there are a couple of different ways to specify which variable you want to do the computation on. One is to use the variable name, so pressure coefficient. Notice I put it in curly braces to indicate that it's a variable name, or I can use the variable number. So if you go into the dataset information dialog, you can see that the variable number for pressure coefficient is 12. So this is just a little shorthand notation. The number 6 in brackets here indicates that I want to use the pressure coefficient values from zone number 6. And this works because zone number 6 and when I did this equation, zone number 13, these are both the same section. They both have the same number of points. So that's one of the important things to know if I'm doing this sort of differencing. the zones that I'm referencing have to have the same number of points. So this has 34 points. This section also has 34 points. So I would not say be able to do a difference between section 4, which has 34 points, and section 5, which has 45. Okay, if see, if I save techplot data for a different time in a different techplot file, can I extract polyline data over the different techplot file? So if you have multiple files, I'm not exactly sure what, I'll try to answer the question as best I can. So I don't quite follow it, but can I extract polyline data over the different file? Yes, so from a script, you could certainly load, say, one file at a time and automate the extraction with a techplot macro. A macro can be written such that it will actually place the polyline and do the extraction, and then say you could write that extraction to a file, and then you could automate that for all files. Is it possible to constrain the slices? I want to cut slices into sub-slices and compute the axial momentum through them. So you can constrain slices, or you can constrain any data using value blanking. Let's do this through the volume data. Volume zone is turned off, so let's turn that back on. And if I go to plot, blanking, value blanking, let's say I wanted to constrain this in the Z direction. Let's look at when it's greater than 0.08 might work for this data set. So here now I've constrained that slice above Z being 0.08. So you can limit your slice that way. I hope that answers your question. If you have further questions about that one, feel free to contact our support staff. Okay, this question comes back to specify equations. Why didn't I have to specify the second term? Why didn't I also have to say 13? Well, that's because I had only this one selected. So when I do this, it's only altering this one. So this V12 is going to reference the zone that is selected. So zone 13 was implied by that selection. Now, if I had multiple selected, this equation should give me an error, because not all of these zones have the same number of values. So you can see incompatible zones referenced. That indicates that it tried to do the math doing a difference between zone 6 and zone 10, which have a different number of points. So again, you have to make sure that those zones have the same number of points. Can you suggest any suggestions to extract lines normal to the surface? This would be particularly useful for surfaces that curve in 3D. No, not necessarily any easy way, no. We can, I think you'd have to use Python to do this. So in the Analyze menu, we do have calculate variables, and you can calculate the grid K unit normal. And then let's turn on vectors to show this. So now I have, this is now showing the normal directions. I think when I did this, I should have put this at the cell center. So this is going to give you self-centered normal. So that's actually going to be in the center of the cell. So make sure that when you're doing grid K unit normal, select cell center. And that'll give you the normals. And then with the Python language, you can fairly easily get the normals for each cell and create a line in that direction. So, and again, if you need help with that, let us know. how do I plot a velocity profile over a line in the way that the journal articles show? So again, I think the way to do the velocity profile would be that slice of a slice, because that way you'll then have a line that goes right along each one of these cells, and then you could plot, say, the velocity values along that line. But doing a slice of a slice and trimmed would be able to get you there. And again, you can do that maybe even coupled with this technique of computing the surface normal to make sure that you have well, slice of a slice is one way, but that's not going to be exactly normal with the surface. So you could create a line that is normal once you've calculated those normals. Again, I think we can help you out with that. Let's see, can a polyline be drawn vertically or horizontally? A polyline is always going to be flat to the string, to the screen. Sorry. And while you're drawing it, I can press the V on the keyboard, and that's going to limit it vertical direction, or on the, and that's going to limit it to the horizontal direction. And then I think it's, yeah, A on the keyboard allows it to be arbitrary. So that may help there. Hopefully that answered your question. Is it possible to extract a boundary surface from the volume data? So let's, the answer is yes, but only via our scripting layer. So let's activate only the volume layer. So I right click, say show selected only, and we'll go into surfaces and say show the boundary cell faces. Oh, I need to turn off blanking. Okay, and so this is the outer boundary. Let's get rid of that polyline. We do have a function in in our scripting language called, gosh, the name is escaping me right now. It's something about create FE volume boundary, but it is available in our scripting language, so you can extract the outer boundary of the volume data. Okay, a couple more questions here. If one makes a slice of the wing, closed surface, and plots it, how do you sort the points to obtain a closed line graph? Yeah, let's go back into zone style and show just the wing surface. So hopefully this will answer your question. If I go into the slice details dialog, let me turn on my slice, and I'll go through the surface zones and extract. This has an option here to extract this slice as an I-ordered zone if possible. So what if possible means? Say I had a wing and a tail. Let's say I had a tail out here and the slice was going through both. Well, we would then have to extract that as an FE line segment, because I have two separate sections and I don't want to see any connection line between them. Here I have just one, say, closed boundary. So let me hit extract. And now I have a closed surface. And we try to be consistent in the starting location. So we try to find I think it's the lowest X, Y, Z coordinate, and that's where your line is going to start. So hopefully that helps. And then thanks, very helpful. Well, thank you for joining us today. Last question, it looks like, can the subtraction between zones tool be used to calculate temporal changes in the domain if each solution time in your simulation is a different zone? Yeah, certainly. Let me load another data set. So again, the best way to do this is going to be through the scripting language, but we can do that if I go into some of the example data we have. Let's go into 2019 R1 examples, simple data, vortex shedding. There we go. So this is, let me make this frame bigger so you all can see this a little easier. So this is simple flow around a 2D flow around a cylinder. So again, if I wanted to say compute the difference from one time step to the next, I would go into specify equations, and let's bring up dataset info. Let's say I wanted to look at pressure difference. Let's call this P-diff. And we'll look at sixth variable, which is pressure. And we'll do zone 1 minus V6 of zone 2, and say do that calculation just for this zone. And then here I would do 2 to 3, and you can see that this is going to get, it's going to cause carpal tunnel syndrome. So you could do this through our scripting language to automate the difference from one step to the next. So again, I could change my contouring to P-diff, and we'll go back to here. Wrong contour group. So now this is the difference between my first time step and my second, and then this is the difference between my second time step and my third. So that's the way you do that. So, okay, well, geez, a lot of questions today. I hope you found it useful. We're at the end. So let me go back to kind of the closing slide for the webinar. So again, thank you for attending. This will be posted on techplot.com/webinars in the next day or two. And again, look for those resources that we're making available. Tutorials, we have a lot of tutorials available on techplot.com/videos, and we have support staff. Pacific Coast, we're available 6:30 a.m. to 5 p.m. Monday through Friday, and you can get a hold of them at support@techplot.com. We also have a European office, which is support-EU@techplot.com. And then if you're in any of the locations that are supported by our distributors, you know, Asia, we have a Chinese distributor, Korean distributor, etc. So you can contact your local distributor. They're going to be your fastest resource for technical support, and you can find that information on the TechPlot website. So thank you very much for your time today, and I hope you all stay safe and healthy out there. Bye-bye.